Hi everyone, this is BIT2400. We're going to be going, not templates, let's actually get the right link list. I'm just in the wrong part of the file. There we go. What a wonderful start to online lectures. I'm just going to be doing a live video stream of my lectures rather than trying to clean it up and trying to polish it and make it at exactly 5 minute little intervals and have, fancy special effects. Andy Serkis will not be involved in this lecture demo or anything like that, nor will Peter Jackson be doing the special effects. Um, I'm just going to be doing lectures as best I can, hopefully making it as clear as I can. I have a fairly good system down because we actually can record everything that you're seeing on the screen, including live coding. So other than the excessive amount of hand waving that I'm used to doing, you should be able to get a general semblance of what the lecture would normally be. The big thing for me to sort of address the elephant in the room here is while you're watching these videos, make sure you dedicate the time, actually listen rather than checking your phone, rather than doing anything else. Turn off all the other internet connections. Don't check your emails. Don't respond to your emails. Don't look at your phone. Don't let it running in the background. I will try and make it as useful as humanly possible because it will not stick in your head otherwise. And this is coming from experience teaching online classes in the past. When I was taking online classes, even I have trouble focusing for a period of time. So if you need to take a little stretch break, pause it, take a stretch break. If the topic was confusing, pause it, think it through, look at the actual code itself if you need to. The big thing here is don't just assume that you can just watch the videos and it's just going to sink into your head. You have to do these exercises as well. So, with that being said, we're going to look at linked lists yet again. But I was realizing when looking at linked lists or just looking at the slides, there's a couple other little parts to linked lists that we haven't gone over. Was trying to make it fairly streamlined when we first started. Now that we've looked further into the course, and now that I also want to review, how we design things for object-oriented programming, I wanted to spend some more time looking at this before we dove into looking at some other data structures like stacks and queues. So, here is the summary for the term, and I'm actually going to use full screen. I forgot to do that. So, for the rest of the term, our big things are going to be right now. I want to do a number of lectures on linked lists, and we're going to do some live coding with that. Then, either in the same video or in another video, I'm going to do stacks and queues, and we'll implement that. And then after that, we'll look at some standard template library functions. That's things like, we'll also be looking at sorting and searching. So I should also put this in here. And searching. This will all make sense in a bit. Unfortunately, that's the lecture that I wanted to do, sort of, a physical demo of how sorting actually works. That's obviously not going to happen. You really can't sort yourself by yourself while watching a video, so we won't even try that particular part. But I'll explain what we're doing. We could actually sort things in your daily life. I'll think about how we might do that. The videos themselves I'm just going to post them all on a YouTube channel or my YouTube channel on a particular playlist, and then you can just go and grab the videos whenever you have the time to look at them over. This is not ideal. I'm going to be trying to answer questions you have on Piazza. I'll also try and post a way to video chat with me if you want to do that. I'll also make the TAs available for video chats as well. There's still things that are up in the air, and I apologize in advance. How do I explain this? This weekend, my wife and my kids went away to Quebec for just visit grandma. I got a whole lot of my 1400 videos done, and then they came home a day early, and my kids will not let me do any work during the day. So most of these videos will be recorded at night in case I sound kind of groggy and half asleep. That's because I am. Anyways, that being said, we'll try our best. Hopefully, I will not put you to sleep. I'll just be half asleep myself. Okay, so we're going to look at linked lists one more time. We'll also look at linked lists when it comes to templating. I'm actually going to move that up a little level here. So we're going to put that up here. Because templating is kind of a useful thing to look at. So this is the ability for linked lists to be able to store anything that we want, provided it follows a particular set of criteria. All right. And then we'll have a review class. That review class, I'm just going to post a survey for what you guys want to go over, and then we can figure it out. And yes, if you hear something in the background, that's my cat that is hanging around me that decided to just jump up and hang out with me. Still better than the kids talking during the video. Okay, with that being said, we're going to look at some, well, there's not exam. This is a previous slide from from last term. We're going to be doing a quick object-oriented design review using linked lists as our illustrative example. So we're going to revisit linked lists. We'll revisit doubly linked lists, as in it points, we have a previous and a next. That was a child class of linked lists, and since it's a child class, it's going to be me talking through what my thought process is for how I would lay out my code, how I would position things so I can reuse code as much as possible. And it's not trivial by any stretch of the imagination, to the point that today I think I refactored the code myself 2 or 3 times, just like, oh, I don't like that. These are the kinds of things that every programmer goes through. It's not magic. It's not something that we automatically know the right answer right away. If you are flogging yourself for why couldn't I see that right away, you're not going to. On an exam, I need to make it painfully obvious what I expect or how you'd go about this, or give a big hint like, hey, by the way, why don't you try these examples and see how it goes? Just to streamline things. Then we're going to look at stacks and queues, including some stuff I did with my kids to try today and try to get them involved so that they wouldn't be bored. And then we'll live code a stack, and then so hopefully either this will be 1 video or 2 videos, but you'll see it in action. And so also I want you to point out before we get going, the code that you'll see in the slides will differ from what I actually wrote. First of all, because I'm live coding and I'm not going to memorize what was on the slides. Second of all, the approaches can be different. They can both be valid. And third of all, the priorities that we're going with were different between the two. And so there's not one definitive way to make a linked list. There's not something that you just memorize. A linked list or any of these data structures, they follow a particular criteria, a particular pattern, but how they're actually implemented can be radically different. And provided that they follow what you expect, provided they provide the services that you would expect, they're all right. Some might be more efficient than others, but they're all right. And we will see that in excruciating detail, let's say, very, very soon. Okay, so the excruciating detail being the fact that you can change the implementation and it can still be right. We'll see that in action. All right, so here's our linked lists again. This one with Eleanor Roosevelt. Linked lists are just the conga line of data structures, right? You have somebody in front of you, you grab onto them, they don't care who's behind them, they're just walking, you're using the person in front of you to guide you along. So a linked list can be any length. In fact, a train is perhaps a better metaphor for a linked list. It can be pretty much any length, and as long as you pull the front one, it goes in order, so you can go car to car to car all the way down. And and each one of those cars is carrying something. So the idea is, if I want to resize things, if I want to insert something in the right place, how do I do this? Well, an array, if I'm inserting something like, if I have a hospital waiting list, so a queue, in this case would be a queue when we talk about queues. I'm at a hospital waiting room, and somebody comes with a really big emergency, they should go to the front of the queue. I need to be able to insert them early in this collection of data. Well, if it's an array and I insert at the front, I have to move everything back. That's a big, long procedure. If I have 2,000 elements in this array, I have to shift everything over, each node or each element over by one. It's 2,000 operations. It can be slow, and there's an upper limit. The worst thing is if I run out of space in the array, I got to reallocate another array and copy everything over. It's a pain. A linked list allows me to modify the array fairly easily and fairly quickly. So Here's our idea yet again. The linked list, like a train, it has contents. The car itself can carry certain things, and they're hooked up to the one in front. So I have the start of my linked list. My linked list points to the first element in this big long structure, and then you go the next, the next, the next until the very end. At the very end, I have a null. The next points to a null is a null pointer. That's the end of my linked list. Okay. Here's the thing we didn't do last time and that I want to look at today. If I want to add an element, we talked about adding an element just at the end, or you can add an element just at the beginning. What if we want to add an element smack dab in the middle, or some in a particular order? So what I've done for the linked list demo is that I have an insert function, and insert will insert it in the order until it's if you presume the linked list is in order. So it is already sorted. It is every element. The next element is larger than the element before, larger or equal to than the large element beforehand. I will insert this data item at the correct place so that the linked list is still in order. That's what the hope and the dream is. So by adding things to my linked list using insert, I can have a sorted linked list. It's also considered a priority queue. Okay, that's what insert, the new version of insert, is going to do. I still have insert front, insert back, or I think maybe start and end is what I called insert start, insert end is what I called it. So I have those methods, but I also have this new way of walking down my array. I also want a couple more functions for how to remove elements from my array. Okay, so when I want to add this element, let's say here, what do I need to do? Well, first of all, graphically I need to separate these out, but my data itself, I need to stick it right in between, but the real key is I need to change around my pointers. So the new item I'm adding, the next points to whatever the next thing in my list is. So if I can see that, if I can see my pen, this next here, and then after that, then I need to rehook up where this thing right here goes to. So I I'm inserting between these two nodes, this heart node, this lightning bolt node, and so I hook up the cloud node to the lightning bolt node, and then afterwards I uncouple the heart from the lightning bolt and hook up the heart to the cloud. So that's the next step. Boom. And now it's correctly inserted into my linked list. It involves moving around pointers. That's the key to a linked list. So it's fairly cheap. There's only 2 pointer changes necessary, although if you forget like I did this morning, it could be a while finding your bug. Yeah, I had a weird bug this morning. So you want to be, and you may need to go in order to find things, or in order to get every element in my list, or to, yeah, finding things is the real big one. I may need to walk down my entire linked list, and that's a costly operation. So here's what the linked list looks like. Mine, ours doesn't have a pointer to the last element because, well, why? We have a pointer to the last element for the doubly linked list, but for the singly linked list, I saw there was no real benefit to keeping the last. You can't even use the last element most of the time. You can get the front element, you can get the last element, you might as well walk down and get the last element. So ours does not have a last element, you could just calculate it ourselves, as long as we have the front element. Okay, so I have a first, and then I walk down, and I can get the last. A doubly linked list, which is we also implemented, has a first, it has a last, which is special to the doubly linked list. That might be the one difference between ours. And each of these nodes has a previous and a next. The previous can be pointing to null, or it can be pointing to an actual legitimate element. And the next can point to a legitimate element or to null as well. And so you can go backwards and forwards in your linked list, which can be very useful in terms of parsing the linked list or reconnecting things. So what we'll do first, I'm going to talk about iterator classes at a later time. Actually, I might be able to cover it today. But we won't use an iterator. Those are optional for some of the kinds, for some things. I'll point out how they would be done, but I'm not going to do that in the live coding. So I have my nodes. Each node connects to the next node, and I have this list, which is sort of this thing that wraps up all of these nodes. It is a way of hiding. I don't want to know how a linked list is actually implemented. It could be an array. It could be almost anything. It's just something to store my data, whatever that data might end up being. And so the list itself sort of obfuscates, it covers up all the weird quirkiness or how this data is being stored. The nodes themselves are actually where the data is being stored. So um, here would be my linked list node class. First of all, I want to point out the code that we're using here uses the list class as a friend class of the node class, meaning that that list class can directly access, directly manipulate, could directly change values in the node class. So the list can just take a node and just do whatever it wants to with the data because it's its friend. This is like lending your friend your credit card, right? There's a fair bit of trust that you have to put them in the friend class. We didn't use the friend class ourselves. We use getter and setter methods. So here's our node class. The node, in this case, they are using the data itself is a string. Where you're going to use an integer, but it doesn't really matter. When we talk about templates, you'll see why it doesn't matter. In this case, they're using a doubly linked list. They have a previous and a next, and and so all you end up doing is I take in some kind of data coming in here to make the node, and I can get the data. I just return some particular data. Notice this example, I probably should doing this more often. They have a constant for the function name. The reason you put that there, if you remember, I'm just going to slowly say it in case you didn't realize. The reason you put a constant, you can put a constant in your function, is to make sure you do not change your data. If I put the word constant in my function call with the name of my function and how the function is declared, I'm not allowed to change any of the data in that with that function. That's extremely useful when I don't want to accidentally have some weird side effect. So if I'm not going to change the data, you can put a constant to make sure that no data gets changed when you call that function. So here is my character, here's my constructor, and I'm going to check to see if it's an empty string. Fine. I saved my data. And I set up my next and my previous to both be null. As in, I have a node, it points to nothing. Okay. And again, as I said, the friend class sort of breaks this encapsulation principle. It does. The list has to know about nodes and can directly manipulate nodes, and the node class, well, sort of has to be you sort of have to be aware when you're writing the node class that something else can directly manipulate you. If you're writing both these classes and they're really tightly coupled together, this makes sense. So it's only really allowed if they're really tightly coupled. It's the node class itself is just really a place to store the data in this particular case. But because they are working so closely together, it's okay in cases like this. Most of the time, we would not want to do something like this, and so the friend class is normally used with caution, or the friend keyword is used with caution. So here is what we're going to end. So this is what our our linked list looks like. We have a pointer to the front, we have a pointer to the end. Each one of those things actually has some data, some kind of string in there, some kind of a content as we go. The list class itself, we can insert at the front, we can insert at the back. We can remove from the front, we can remove from the back. We're going to do those plus a couple extra things, plus use inheritance. Yay. And we can print everything out, and we can see if the linked list is actually empty. Also, notice if you want to get kind of lazy on things, it's not lazy. It's considered efficient. It's just yet another way of doing things. If in my header file, if I know that this is a very simple function, I can just put the actual function definition in my header file. It's only for really simple function definitions like this one. All right. So if I'm inserting at the front, what the heck does that mean? it means I need to check to see if I do have something at the front, if I do have a node, and then I need to hook up the pointers from whatever new node I'm adding. So I'm going to make a brand new node, and I'm going to hook it into my linked list. So when I'm hooking it into my linked list, I have to check to see if there is something there, and if there isn't something there, right? So the first is equal to the last, which is equal to this new pointer. Um, Otherwise, what I need to do is change my pointers around. So it looks like this. So here's my original linked list. Here's this new thing I'm going to be adding to. So this is just the pointer to the node structure itself, right? I have pointers everywhere. And so all I'm going to do is new pointer. I'm going to take first pointer. I'm going to point it to 12, and then I'm going to point this node structure at the 7. So the 12 node structure is going to be pointing to the 7. I just change my pointers, and then I'm good to go. I don't need to worry about new pointer, but I just added 2 new pointers. I just changed one pointer and added a new pointer. If I'm going to insert at the back, again, I need to check to see if I have an empty linked list. That's always bites you. And then if I have an empty if I don't have an empty linked list, then I change my pointers. But in this case, I need to find out who was before the. Let me see here. I find the last element, and I hook up the last element to the new pointer. That's fine. And then the new point, yeah, that should be still work. And then I change what last points to this new pointer. All right. So here's what it looks like originally. Here's this new pointer. I change what last points to. It points to this new pointer, and whatever. So the first thing I would do is point this thing to this. That's step 1. And step 2 will be this. Right? I would do it in that order because I can find the last element quickly. I have a pointer to it, and then I can point where that last element points to next. It makes my job easier. So removing from the list from the front, maybe not easy. I need to, again, I find the new node I'm looking for, so I want to find out I got to get the value. If I'm removing from the very front of my array, I don't know why I have a value here for the remove from front. There seems to be no reason for having a value in here. Anyways, we're not even going to be doing that because they're deleting the pointer immediately afterwards. Oh, it's I'm returning the value. I didn't notice that before. All right. So what I'm going to do is I'm going to find the very first. I'm going to get my very first element right here. If the first is equal to the last, well, then I have some problems because I'm going to delete both of them. If they're both null, I don't have to do anything because they're both equal to null. If I do one or the other, and this first is still pointing here, right? So if they're both equal to null, or I only have one element in my linked list, both of those cases, I'm just removing this, and I probably should, instead of saying 0, it should be a null. It's the same thing, but I want to be consistent. All right. After that, I say that the first is equal to whatever the next was going to be. Fine. And so in the case when I don't have them, if I have more than one element. And then afterwards, what I need to do is I change my first, and beyond that, what did I need to do? Did I need to change null pointer, get the data, that's a particular value. I can delete the pointer. There is a problem with that. Oh, there's my is empty. If it's already empty, then I just return false because I can't remove anything. So that's already covered. I get my data, I put that in the value, I delete my pointer, I delete this node, and then I return. All right. So what does this look like? All this is going to do is I'm going to point first pointer to this 7. So it's going to be this, to this in the end. And actually, you're going to see it right now. Boom. Okay. And my temp pointer is still pointing to this thing that I had, the original pointer that I had at the start. So all I did was change my first pointer around, and the temp pointer is around, and I can pass that back out of the function if I need to. But there it goes. So if I'm removing from the back, okay, that's going to get a little bit hairier. So we won't go line by line through the code here. I need to figure out if it's empty, because if it's empty, I'm not removing squat. After that point in time, if I'm going to check to see if the first is equal to the last. If so, well, I'm done. I just return. There's nothing to do. I just get rid of that one particular node. Otherwise, I need to find the second to last element. I find the second to last element, the one that points to this last element. And if once I find that, then I can, in this particular case, I walk down my array until I get to the very last element, the second to last element, and then I point the last to the second to last element, and then just get removed from the element that I have. Okay, and then unhook up essentially what the second to last element was. So it's going to do this. I'm going to walk down. I'm going to have to find out where that 11 is. Oh, remove back didn't show something. Okay, there you go. Remove from back. I go to the 11. So I need to walk down my array. I know where the last is, so the second to last, I find where the 11 is. And then I need to point last pointer to that 11. And then I'm going to get rid of the pointer to the 5 and just say I have a point to null. So that's what that's going to do. So I change my last pointer, point it to the 11, and then I get rid of what 11 points to. Fairly simple. The current pointer ends up pointing to 11 at the end. And then I can get rid of it. We don't need to do print because all we're going to do is walk down our array, and every single time, as long as it's not equal to null, I just keep on printing out the data for each of those nodes, one after the other. One of the things I don't like about this set of code is that we keep on directly using the data rather than calling functions. I like a lot of function calls simply because it allows me to do some interesting things. And then we have destructors and constructors as usual. But let's get to the real fun. I want to get to my actual code. So let me jump to. We can insert to the front, insert to the back, remove from the front, remove from the back. Great. What else should we be able to do? Well, we'll look at an iterator in a second. So let me do the live code thing first, though. So here we go. I'm going to keep this, and we're going to get to this code. Hopefully this is the right one. All right, great. Here's my linked list code as I had before. And if I go to linkedlist.h, hopefully it'll be a bit more obvious. It's a lot more convoluted than the other code that we were just showing, but it also does some more stuff. So a linked list node has a start. It does not have does not have a end, right? The doubly linked list has an end, but the first one doesn't. We also have this type, which is just for me in case I want to see, like, hey, is it the doubly linked list or is it a normal linked list? We can just keep a type around. I have some methods, like this is a protected method for finding a particular node. I might want to actually use this. So based on an ID, can I return the particular node? Can I get the last node? So this is a virtual method to get the very last node in my array. Might be useful. Here's my public constructor. I have a destructor. I have a particular type, just in case I need that sort of thing. I can insert at the start. I can insert at the end. Notice these are both virtual functions. Why do they need to be virtual? Because if I have a doubly linked list versus a normally linked list, the doubly linked list has some extra stuff it needs to do. It has a first and a last pointer. It also has to deal with the previous and the next pointers as well, per node. That means that you have to do things a slightly different way, and anytime when you hit a scenario where I don't know what's going to happen with the doubly linked list versus this one, or I need to do something special for the doubly linked list rather than the linked list. I need to have a virtual method. A virtual method, again, is when I call this function, it will look up, hey, which version of this function am I supposed to be using? Am I supposed to be using the parent's version of the function? Am I supposed to be using this version of the function? What am I using? So if I have a pointer to a linked list, some kind of linked list, you don't know what kind of linked list it is, and so please bear with me with any of emails that are popping up. Um, I'm calling insert start, for example, on some linked list. Now, it could be a double linked list, it could be a singly linked list. If I call insert start, it's going to say, hey, which function is it for, or what kind of class are you? So I will go to a virtual table per object. Every object will have an access to this virtual table, and it will say, oh, where is this insert start defined? Oh, it was defined in doubly linked list. I'm going to go there for that function. It allows me to call the right function based off of the object it's being called on, not based off of what type of pointer it is. Okay, so we can go review that lecture if that's still confusing people afterwards. I have another function here, which is just called insert, and that's not even a virtual function. Actually, these three are not virtual functions at all. This is another form of polymorphism. It's the same function name as insert start, right? But all it does is it takes in an integer, not a linked list node. The reason I have this is all this is going to do is make a node based on that ID and then call insert start, this insert start up here. The reason I want that is just in case that I'm calling a function and I don't want to have to be I found myself keep having to call the code and then going, oh no, but I've created the object too early and I need to call this version of this function or this version of that function. Instead, I have this node that I'm going to insert. I don't know where, I don't know how yet, and I can once I have it broken into this way, all you need to do is pass me in a number. It'll make a node, and then I insert the node afterwards. And inserting the node, I don't have to delete the node or recreate the node. It was the code looked a lot uglier before I broke this down. Also notice that insert, when I'm just inserting a node in order, it doesn't need to be virtual because I still need to walk down my entire array, and then I'm going to insert at a particular position. In fact, there should be, I should have one other function in here. Maybe I don't. Oh no, because it's going to be the function's actually in the node, where it's inserting, the nodes know how to insert themselves relative to each other. So I had the nodes insert themselves versus having the linked list inserted. So insert at a particular position, it doesn't matter if it's a double linked list or not, that's going to work properly. Okay, then I've overloaded the plus operator to just insert at the end of my doubly linked list. We've done that in class. So when I call plus on it, all I do is call insert this plus operator. All it does is calls insert end. Okay, then we have a print list, which we've went over before, and which is virtual because it's going to print out things differently. And then I have the length of my linked list. That doesn't have to be virtual at all, but it could be. But in this case, it doesn't have to be virtual at all because it's just going to walk down my array. Okay. I'm also going to have to fill in these three functions. These functions have not been defined yet. So the remove functions. So how the heck do those end up looking? So here's the linked list class. And we can go down to each one of these parts. Again, operator, all it does is call insert end. Fairly easy. All right. Insert start, for example, it makes a new node and then calls this version of insert start because I want as many conveniences as I possibly can. If I want to insert just based on a number, it works. If I want to insert based on passing in a node, it works. In fact, it does the same thing. It goes through the same mechanism, but it gives me more convenient methods, right? It's paying by cash or check or credit card, right? The more ways I can pay, the easier it is, potentially easier it is for me. So that's what these are. These are effectively convenience methods for inserting things. Here is where the fun really begins. This is my new version. I'm going to insert in order, unlike before where I was just inserting the front or the back. So I see if if the start is equal to null. I should maybe called is empty or something like that instead. But I'm checking to see if the start is equal to null, and if it's equal to null, I'm just going to call insert start, this other function that I'm going to use. Insert start just inserts a node at the very start, and it will that particular version of the function will handle whether, how everything is hooked up. But I know I'm inserting at the very beginning. If it's empty, I'm putting it at the front. There's no front. All right. Otherwise, what I'm going to do, I'm going to keep on walking down my list, seeing if the thing I'm going to add is can evaluate to being less than the current node. And each of these nodes, that operator will check to see, hey, is this node I'm adding, is the contents, is the data being stored less than the contents of the data for current node. If I find that this is in fact the case, then I need to insert. I'm going to call it insert after. Insert after is this function that just the node itself, it inserts the node after the previous node. So previous node, I'll insert to add immediately after previous node, and then do the hookup for all the various, whether there's other elements. Or if there is no previous node, as in previous node is, it starts off at null, and as soon as you walk one step down, I'm just keeping a tally of what the node before it was, right? So when I change current node, I'm going to walk current node starting at the very beginning and walk it down. I'm going to walk down my linked list. I'm going to keep track of what the node before me was that I've already encountered was, just in case. The current node, if previous node is still null, it means that I'm inserting at the very front of my array. Oh wait, insert at the start. Makes my life easier just to call that function. And then afterwards, I'm going to keep on. I change previous node to being the current node. I change the current node to being the next, and I'm just walking down my array, or my linked list. If I get to the end of my linked list, well, now if previous node is equal to null, I got an empty array essentially. There's nothing in there. So I'm just going to insert at the start again. That shouldn't ever happen, but just in case. Otherwise, because the current node will never be equal to null at the start if it's an empty array, and therefore I should never get into that case. But I like being paranoid. Otherwise, what I'm going to do is the previous node is equal to null. Let me see here. Oh no, I could have a single element in my array in my linked list. So the previous node is equal to null. The current node is has a single element. It's not equal to null. Actually, it's still going to do one step, and so previous node is still going to be not null no matter what. Okay. Anyways, if I get to the very end, I'm just going to call the insert end function, just insert the node at the end. Easy enough to do. So I don't even need to do that check for the previous node. In fact, let's get rid of it, just make my life easier. Okay, and there's no way that that's going to work. All right, here's insert start. I insert the node. I take the node I'm going to add. I insert at the start. I change the start to point to this new node I'm adding. That's it, right? I'm trying to let the nodes sort themselves out. So to add inserts itself. I'm inserting pstart after to add. I could manually hook it up, but I want to let the nodes sort of do it themselves and for my implementation. Here's me inserting at the end. I find at the very last node, I call the current node, insert after, the thing I'm going to add, and the only way that I could possibly add it at the end, so on the off chance that you try and add at the end, but there is no last node, if I call insert end and there is no last node, I insert it at the start. That's it. Okay. But notice, maybe you didn't notice this, but maybe you did. For a doubly linked list, I need to update the last element as well. Insert end only works in this case because I don't have to also works this way because I don't have a last element to update as well. If I go to my doubly linked list versions of these functions, so here's the doubly linked list version of it, insert end, I call insert end for linked list, I call the parents version of the function, and then I update what pend does, because otherwise it doesn't make a lot of sense. So I'm just calling the parents version of the function, which does most of the work, and then I need to update one other number, which is this thing here. Here is me inserting at the start. If I'm inserting at the start and if the start is equal to null, then the start and the end are both going to be equal to whatever this node I'm adding is. Otherwise, I'm just going to call insert after for the. I'm going to call the. Let me see here. I might want to just call the insert start thing. I'm just trying to figure out why I needed to do it this way. Or I might have just reinvented the wheel for no apparent reason. Yep, I think that's me reinventing the wheel for no apparent reason. Yep, okay. So the only possible thing I might want to do for this instead is I might want to call insert start, because maybe I want to actually do the parent version of this. So linked list, : insert start, and to add. Okay. If I do this, then the to add, then it's going to be inserted at the right place, and nothing needs to change at all as far as I can tell. The only possibility is, I think the only possibility is if I'm inserting this into place at the start, and no, and there was a node beforehand, it's still fine. So yeah, I don't even need to do any of that. The only problem I had was if I tried to insert it at the start and there was nothing already there, I needed to add this thing. So I'm going to get rid of this and just let all of that, my parent, do all the heavy lifting. Okay, we're still going to have some problems. Alright, so here's me inserting at the end, here's me getting the last node, here's me printing the list. There's also, like, I can use, what I'm trying to do, if you hadn't noticed, is I'm trying to avoid rewriting code. I'm trying to avoid doing the same thing as I did with the linked list in the child class. If most of this stuff is being done in linked list, I don't want to redo that same work in doubly linked list. Okay, so we looked at, and we can also look at how this cell is going to work now. So I'm going to start it up, and hopefully it's not going to break or anything. Break point, so that's not so bad. Let's have a look. Here we go. So I am actually going to be adding the numbers 4, 17, 2, and -3 to my linked list, single linked list. And after I've called insert, the insert that's going to go in order, I get -3, 2, 4, 17. For inserting for a double linked list, 2, 5, 4, 3. Inserting for in linked list, I get this. I have an extra step in there. For my doubly linked list, 2, 5, 4, 3, I get 2, 3, 4, 5. This is what the doubly linked list has and the order it's in. The thing is, when I'm inserting elements, it's being inserted in the correct order, which is what I was hoping for. That's great. Let's figure out how I can remove nodes. So, for my linked list, I want to go back to my linked list here. I'm going to have these 3 remove functions. So let's go over how those actually will look. So let me go down to the bottom here. That's where I stored them. I'm going to remove an ID based, I'm removing an element based on the ID. Again, I'm trying to avoid replicating things. So what I could do is I know I already had a function that finds a particular node. So again, I can use this if I want to be lazy and I don't remember what the name of the function is. Find node, and it's going to take in an ID. Okay, I don't need the word this in front of it, so let's get rid of that. So I'm going to ask to find a particular node. Uh, if that node happens to be null, well, I know I'm not going to be removing that particular node. Fine. Um, if not p found, or you could say, sorry, found, or I could say if p found is equal to null as well. Well, if I didn't find squat, I'm not gonna change anything in my array. I'm not gonna just remove some random element. I'm just gonna return null. Okay, I might want some kind of error message, but maybe not. All right, what else could I do? Well, I want to, once I've done this, let's have a look at what I could do here. I'm going to remove this. I'm going to find that particular node. I found it. I need to remove where it is. So what I might want to do is figure out who is before it and who is after it. Now, with a doubly linked list, that's going to be a lot easier because I can figure out what element was before it. Uh, Without a doubly linked list, I might have to figure out what I need to do. So what could I do? I might have to walk down my linked list again and find the particular node that I'm missing. So print list, find node. Yep, I'm going to have to walk down that stupid list again. Get the last node. Yeah, I have no way of doing this. So I need to, uh, what I might want to do though, let's try this. I need to get the previous node from pfound. So what I could think, what seems reasonable is having some kind of private function that if I pass in pfound, it finds the element beforehand. If and if the pfound was at the very beginning of the array, it would return null. Okay, so let's do that as a particular function because I'm going to need that functionality so that I can hook everything up. I can find the element after pfound. I just call pfound the next get next, right? I can get the next element after pfound, but getting the previous one in a linked list, I can't do that. So let's make a brand new function, and let's see if I'm going to put it in my private stuff. Um, get previous node, and then linked list node n. All right. I'm going to go to my linked list node, and I want to put this. I'm going to put it around where I was going to be, where I'm going to be using it. Turns a pointer to the node just before n. All right. All right. So I'm going to have a while loop. While p cur does not equal null. Let's also do something else. So if if you give me a node that doesn't make sense, well, that's fine. Um, if pcur is not equal to null, then what I want to do, and pcur does not equal pcur I want to make sure that if I can find pcur, I I want to check to see if it's not equal to null, but I'm hoping it's never going to actually hit null. We're going to stop it when pcur is the step just before n. So so I have pcur, and I need to actually give it a name. So ll node star pcur and get next. So, and I can just check to see if it's actually equal to n. This is a pointer, like, is this pointer equal to this pointer? That is perfectly legitimate given what we're trying to do here. But we could also say getting that particular node and seeing what the ID is. But this way, if it could also be equal to null here, but it doesn't really matter because if null is equal to not going to be equal to n. Okay, so if I have a while loop here, and I'm going to check to see if that's going to work. I'm going to also check to see how that works. Okay, I like putting extra parentheses in things. All right, so if it's not equal to null or this, I'm going to say p cur is equal to p cur get next. I'm going to keep on walking it down until I get to what I'm looking for, and then if p cur next, if the pcur.next is not, so as long as we know it's not equal to null, then we can just return pcur. So we know it's equal to the node that we're looking for, and so if this is in fact not null, actually, if pcur, if it's equal, if pcur is not equal to null, then I know we found what we're looking for. Heck, I think we could just return pcur actually, because if pcur is not equal to null, if pcur is equal to null, I want to return null. If it's not equal to null, I want to return. I need to return. No, I wanted to return pcur. That's fine. So if pcur is equal to null, then I want to return null. If pcur is not equal to null, it's an element just before what I'm looking for, which is exactly what I wanted. I can just return pcur, and I'm good to go. All right, here we go. So if I've the thing I'm looking for, I've found the particular node. So if I've not found it, then I return this. Otherwise, I'm going to say I want to get previous node. And I want to pass in the p found. So I want to say I want to get the previous element, fine. And then what I need to do is, so I found the previous element, I found the element I'm going to try and find, I can find the next one afterwards, and so I need p previous. We also need to figure out if this is the last node if the node we're trying to remove is the last or the first element, what do we do? And so if p previous, then it can't possibly be the start. And if it's the if it's the last, then I need p previous. Will be pointing to p previous. Okay. Okay. So p previous set next, and that's going to be setting it to p found get next. Whether it's null or not, it doesn't matter because that should work. And so I'm changing what p previous points to the one I'm bypassing the node that we're finding. I need to figure out if the node that we're finding is actually a legitimate node. If p found get next, if the next node is not equal to null, then I know that it's then we know that p found was not at the end. So if there's a next element, we know it's not at the end. Therefore, we also can say p found set. Oh, I don't need to do set previous. This is going to be something that we're going to be that we can try out with so if double linked list, then need to set previous. But otherwise, if it's doubly linked list, and so if this is not the case, then the last element that we have, we don't have a last element either, so we're fine. We're good. I have the previous, it's pointing to the one immediately after what this thing is. Okay, I'm done. Hopefully. Alright. And that should remove that. So I'm just removing it based on a particular position. Let's remove the very first element. So I'm going to remove the start element. It's always going to be the start element. So I need to figure out p start is equal to, oh, and I need to return after I'm all done with this. Return p found. There we go. I'm going to remove the element from the very start of my array. So this is equal to p start is equal to p start. Oh, I need to keep a track of what p start is. Okay, so p start is the new p start is going to be equal to p start dot get next, and then I'm going to return my p old start, and then I'm good to go with that. I'm just removing the front element of my list. If I have nothing left in my array, then if there's only one element, then p start's going to point to whatever that next was. That next is empty, so we're done, and so that's fine. I have an empty list now. So I also need to figure out if p start is equal to null or not, I think, because otherwise I can't call get next. So if p start, and so if that's not equal, if p start's pointing to nothing, then I'm going to return null. There's nothing to do. I have an empty array, I return nothing, otherwise I remove the first element. Okay, and here's me removing at the end. I want to have if p start return null. Alright, next I'm going to figure out what the last element is. I need to find the last element. I should be able to get the last element, and I need to get the one just before that, and then get rid of it. Okay, so this get last node. All right, and then I can get, so if we know that this is, this should be a not. Great. If we know that the last is in there, when it should be there for sure, so I can do, let's say, an assert. We need to make sure that it's not null. But since it's not an empty list, we know that p last, there has to be a last element, even if there's only one element. Okay. I want to get the previous node before that. Previous node, and I'm going to say p last. I'm going to get the previous node. If that previous node happens to be null, then we know we only had one element in this silly array. Or I can also say if previous and if p start is equal to p end, for example, then or p start is equal to p last. There you go. If p last is equal to p start, I only have one element, so p start is equal to null. Yeah, is equal to null. That should be fine. And otherwise, what else do I need to do? If the last element is equal to the start element, okay, so last element is equal to start, I only have one element. Other options, I already checked to see if there's no elements at all. Final options, I have one other element, and I know that p previous should be, so I can actually even do an assert on this one, p previous. I really have to have a previous element. If I have more than one element, there's always going to be a previous. So I'm just going to assert this just to be, if something was wrong with my data somehow, I want to catch it early. So my assert is equal to previous, and then what I need to do immediately after that is I want to figure out, so after I've done this part, I want to see if I want to be able to just remove that previous, that next part. So p previous, and I want to say set next, and I'm removing the last element, so set next, and I'm going to set that to null. So it's the previous element's pointing to nothing, the last element's sort of effectively removed from this whole thing, and then I can, at the end of the day, I want to just return the last element. So return p last. All right. Is there an option to return other stuff? Let's find out. But in all cases, this is the element I'm removing, so I want to make sure that that's fine. All right, that should do it. Let's compile it, and hopefully... All right, let's also check out my code. Let's play around with this a little bit. So we had some old code in here. We've deleted some stuff. I want to do... what could I do here? Let's do... So we're printing the list. I'm also going to a lists position I, remove, let's do remove from the end. And I'm going to do print list again, and then we'll do one more. Okay, and then a list. I always know I happen to know that I always have 4 elements in my array, so my linked list. So remove start. We didn't get the chance to really play around with this and see other ways of doing this, but let's see it in action. All right, so we have, I want to make sure that my thing is not being overly ambitious. Yeah, it's being overly insane. I got a bug in here somewhere. Something for me to look into it a bit more. I'm not going to go deep diving into this. I'll stop the video and see where the issue is, and then point it out in the next video. But for some reason, I've uncoupled. When I tried to remove the last, I ended up removing the very first. I'm assuming I just removed from here, between 2 and 3, versus finding the very last element. And that seems to be what's causing all my grief here in these cases. So I want to see if, yeah, and this one, same thing. It goes from -3, 2, 4, 17 to just -3. So I'm going to look into that bug in a little while, because I don't want to do it live right now. I want to briefly hit up, what I'm going to do is I'm going to finish off what we're doing with iterators and linked lists, and then I will look at stacks and queues at another lecture. Then we'll do a review of the code for the stacks and queues after that. So here is an iterator, and which is very similar to what we were talking about with linked lists. So so far we can insert at the front, we can insert at the end. What if I wanted to do the middle? Now, we did something involving a searching. So you don't have to use an iterator. My approach that I was showing you doesn't use an iterator. The idea of an iterator is, what if I have sort of your finger as it's going along, if you're trying to read and you're using your finger to follow along where the words are, or the bookmark on your page when you're reading a story. The idea is an iterator is a pointer pointing to the place where you currently are. It points to the node that you're currently looking at, and then you can go to the next or the previous one at any given time. So the iterator just allows you to point to where you are in the linked list, and you can move to the next one, much like you following along with your finger. So it also allows you to compare iterators at the same time, which is a really nice thing to be able to do. So you could say, like, is this iterator equal to this one? We can also make it so that we just return an iterator. The point of all of this is I don't want to know how a linked list is actually implemented, and an iterator allows me to avoid all of that. Because it is purely pointing at somewhere in the array, I don't know how it's being stored. I just say go to the next one, go to the next one. You don't have to, when you're pushing next on a DVD, you don't have to know how it's doing it. You just push next. The iterators, you just go next. So that's what the general principle is here. So here's my linked list as before. Here's my double linked list as usual. And here's what we did last time. So the iterator is just pointing to where we are in this linked list. And as I walk down this, and so I can have my iterator class, I can get the data, whatever the data is. In our case, it was an integer, but in this case, it's a string. It could be anything, some payload that's on your linked list. I can go to the next, but you don't need to know that there's this node structure. I just say, give me the next one, or give me the data that I'm currently pointing at. But the person using an iterator does not need to know how it's being done or what's in my linked list. I can check to see if two iterators are equal to each other to make sure that if they're one and the same, that sort of thing. And also with it, so here would be an example of an iterator being done. Here is me getting the particular position. I start off position null. I can get the data for something. I say at this position, get me the data. The position is the node that I'm looking at. I can get the next. So if the position is not currently equal to null, I go position next. So just move it one step over. And I can check to see if two things are equal to each other by saying, is this position equal to this other iterator's position? Here's the kicker, that the thing that seems to, for me at least, makes iterators make sense, or why they're so important. Right here, I may not be able to show it properly. Right here for the beginning and end, I can just ask the linked list, hey, give me the iterator that's pointing to the front of your linked list or at the end of your linked list. Now you don't have to know what the first node is or the last node is, or that there are even nodes. You're passing around iterators, and the iterator allows you to abstract away all of that information. And you can just start again from the very beginning. It's a nice little design recipe or design pattern to allowing you to iterate through things. And it's actually what's used in the standard template libraries. You don't have to manipulate the data, you use an iterator to walk through things. So here's begin. All I do is make an iterator. I set the position to be the first. I return the iterator. That's it. Right? Here's me making an iterator. I find the last position, or I find, yeah. If I want the end position, this seems a bit odd that it's the iterator position is equal to null. I sort of want the last position, so I would like to actually set the position to be equal to walk down my array and get me the last element and put it in there. If I want to insert something in the middle, I can use the iterator to walk to the middle element, or a particular element that matches a set of criteria, stop there, insert my value there. And we can look at that if we wanted to. And if I wanted to erase a specific element, the iterator allows me to find that element. Versus me passing in a linked list node, I pass an iterator so that anyone using this thing, they don't need to know how linked lists are implemented. All right, so I can insert the back, insert the front. We can leave that alone. When we come back next time, we'll look at stacks and queues, and hopefully I'll be a bit less sleep deprived. We'll look at stacks and queues, and including, I'll give you a little hint of things to come, including pictures taken by my kids. Yes, fun times. Some fun times to be had. All right. With that, I'll take my leave of it, and thank you very much for listening, guys.